Hello, thank you very much for inviting me to the GeoDict user meeting this year. I will talk about permeability and percolation of sea ice, and this is a collaboration between Norwegian University of Science and Technology, the WSL Swiss Federal Institute for Snow and Avalanche Research, and Math2Market. The talk is structured like this. I will talk about sea ice and climate, permeability and calculation, then introduce how we describe how we apply this to sea ice digital rock physics, show some results, discuss the percolation aspects, and also show you the data that will be available, and finally close with conclusions and an outlook. Sea ice on Earth. 5 to 7% of the Earth's ocean are covered by sea ice, and it plays an important role for climate on Earth. But the properties of this ice are difficult to measure in the field, and therefore the potential to take samples and scan these is very important. One process that I like to describe related to the properties of sea ice is the melt pond albedo feedback. You may have heard about this. During summer, the snow on the sea ice is melting, and then it depends if this melt water, does it flush through the ice and exposes a bright surface and reflect more solar radiation, or does this not happen? Here on the right hand side, you see the albedo evolution for several years measured in the Arctic. Here you see that the melting starts, but there's large uncertainties related to this process. Here you see the melt pond coverage. It's quite large during summer in the Arctic Ocean. Sea ice normally, here's a vertical section of how sea ice looks like. It starts normally growing at the top with a granular interface, but then becomes very soon a columnar material growing downwards. What you see here are brine channels. So sea ice includes a lot of salt in the beginning, but much of this salt also drains off. And this process makes the water below the sea ice more saline. It drives ocean circulation. And so we try to understand this process better, and also, of course, the size of the pore networks and the connectivity and how they will drain and flush meltwater. A look onto sea ice ocean interface is interesting. Normally the ice is growing there with a lamellar surface, but after a while you get different features, and from these primary pores you get the evolution of secondary pores. Here's actually a micro CT image of the sea ice surface looking from you look now from below on the ice surface, and there are a lot of features related to the growth process and growth mode, supercooling, and so on. So just to give you an impression how sea ice looks at the surface, when sea ice becomes older, here on this side you see still this lamellar feature on the left hand side of young sea ice. When sea ice becomes older, you get larger brine channels that you see here. And this is of course important when we want to image sea ice. We always have to choose the right field of view. Here, of course, one would say, okay, here the field of view of maybe a few centimeters is enough, but here it may be not enough, because the brine channels, the large channels that evolve, can have much larger spacing. In the present talk, we will be concerned with the young ice, so where not much of these large channels have formed. Percolation. As you know, percolation describes the emerging properties related to the connectivity of a medium. And most studies to date are based on isotropic percolation, where you can choose any direction. In nature, under the driving force of gravity, percolation is often directed. And then it's only one direction that the path is allowed. And this is actually the case that sea ice should belong to this class. We will later see that it's quite important and that the results indicate that indeed sea ice is a directed percolating material. Yeah, percolation theory then often describes a property in terms of P stands for porosity here, and PC for a critical porosity. A formula like this with an exponent that depends on the property, also the dimension, the direction, if it's directed or not. And so this approach we will also make in this paper to find a solution for the permeability of this form. Digital rock physics for sea ice is actually based on the following steps. First, of course, we have to do field sampling. Here you see in the background Longyearbyen on Svalbard. This is sampling for the present study. Here you see where the ice cores were taken out, quite close to each other. Then in the present study, we centrifuge out the brine from the ice. This is quite important because otherwise, when you store the sea ice at different temperatures, it will change its microstructure. So we centrifuge it at in situ temperatures. Then it's scanned by computed tomography. And then finally, analysis and simulation with the digital rock physics models of GeoDict. The field work for the study, as I already showed, it's here, is the place. It's 1 kilometer from Longyearbyen, thin ice in a fjord about 35 centimeter thick. We know that this ice froze up in the middle of March, and then there was a cold period. Here you see the temperatures. Up you see precipitation and wind velocity. Yeah. And then the temperature was rising, and when we were doing the sample, the temperature was a bit higher, but quite stable, and some snow had fallen onto the ice. Ice cores that were taken out, I show you here in the middle, you see salinity. Salinity is a conservative property. If we now change the temperature to a different value, then the salinity will be the same. And these are the cores that are analyzed. You see salinity is very similar, which is important for our approach here, because we now take these cores that had an in situ temperature, which is shown in red, and we cool them in steps to lower temperatures. In this way, we can extend the porosity regime that you see on the right-hand side. This was in situ porosity, so we extend porosity down to 2 to 3% for the bulk samples. Then the next step is the X-ray computed microtomography. Here, as I showed just as a sketch, you rotate the sample and take many images, radiographic images, and from these, the interior of the sample is reconstructed by mathematical algorithms. What you get out then is a 3D sample of absorption values, normally as a gray level image, and this we have to segment into, in our study, air, ice, and brine. You see that the contrast between air and ice is very good. Between ice and brine, it's not good, and it's there's no clear, no really good working segmentation algorithms because the contrast is so small. We were here using the OTSU to segment air and ice, and then something that is called triangle algorithm from ImageJ. And this gives reasonable values for the brine content. Yeah, but as we centrifuge the sample, we focus mostly in this study on permeability on the connected pore space, and this will be the air pores that are emptied for brine. So this centrifuging is shown here on this side. Effective brine porosity, you see here, this is the centrifuge porosity, and here's the total porosity. And you see that this these data show a kind of equation of this form with a threshold porosity between 2 and 3%. So if we get below our values, at values lower than 2 to 3%, we would not get out, centrifuge out any brine. Here are some calculations that show where the maximum exponent in this equation is. Yeah, the equation is kind of effective porosity is phi minus critical and then with the exponent 0.83. This is an important result here because it gives us the possibility to look at the large samples. These are 7 centimeter diameter samples, and for the micro CT we go to smaller samples, but we always take this as the background for our critical porosity. How do connected and disconnected pores look in a micro CT image? This is a segmented image, and here you see the total image. This is actually cut out from a larger one, from a larger scan, and just this shows some examples here. The red is the disconnected, the connected pore space. The green is the disconnected. Yeah. Here on this side, disconnected and connected pores are about the same. You see, this is a horizontal section. So you look now down into the ocean along in the vertical direction. So in the horizontal, here much is connected, and here is only connected in the vertical. And in the horizontal, there are almost no connections here again. The pore size, of course, depends on the temperature or depends on porosity. And here it's indicated the temperature dependence. Yeah, this is a median. This is a distribution of open brine pore diameters. And here on this side, the pore throats. They are quite similar, but you see when the ice becomes colder, the pores shrink. And at some critical value, these pores shrink and disconnect. Here are now the results of the permeability simulation with GeoDict. It's for 150 images, 3D images. The gray regime here shows where the porosity regime approximately 2.5 to 3%, where we both have permeable and impermeable samples. Above 3%, all samples have been permeable. 2 fits were done to the data. One is a classical fit where permeability is just proportional to porosity with an exponent. This exponent is 4.0 plus minus 0.4 in this fit. And the other one is a percolation fit of the type porosity minus critical porosity, also with an exponent which is then a bit smaller here. You see there's quite large scatter in the permeability simulation, and this is related to finite sample sizes because in some of the samples we have larger brine channels. That's something that we will see in the next sample. Image. The sample sizes here are finite, and there are some larger channels, as you see here in the mid sample, for example. And these are not always running through the sample. Sometimes they are running out at the sides. And so in this sense, it's statistically representative what we do here, that we compute the permeabilities, but we have a few large values. And if there would be more of these large brine channels, then we probably would have needed larger sample sizes. But I think here we can be confident because this is young ice and there are not many of these large brine channels. Here also an example of a 3D sample splitted into an upper part where this larger sample brine channel is running out at the side, and here at the lower part it's not running out at the side, and we get then the permeability. The red here are the through flow path. The other part of the pore space is not connected. Here you only have this connection. So what is the cause of the permeability threshold at about 2 to 3%? To do this, we have plotted here the median throat size based on porosimetry in GeoDict and the maximum path diameter. Maximum path diameter is quite scattered because sometimes you have necking in the brine channels and the channels that go through. And also, as you see, the green here is about 2 times the voxel size, which should be the resolution limit for our study, and we come close to this. But the throat size, it's quite a good relationship here, and we see the throats are decreasing with porosity, with lowering the porosity. And here at the percolation threshold, the throats have a typical width of 70 micrometer. So that's where we actually observe that the channels disconnect, and therefore the whole pore space becomes disconnected and is no longer percolating. Another interesting, here I show you the same image again, the throat size, but in contrast to something that is called specific surface area length scale, which is 4 times based on cylindrical pores, which is 4 times porosity divided by specific surface area. And this is actually showing critical behavior, because here not simply the diameter of the channels is shrinking, but they are disconnecting, and therefore you get an increase in specific surface area, you get a decrease in the nominal specific surface area length scale. Percolation is also an important parameter, is the correlation length, and the correlation length is the separation of the pores. Also we take it as separation of the pores in the image. Here's the sample size. So you see that at low porosities, we are at half of the sample size. So the reliability is a bit limited in this regime, but otherwise we find a critical exponent of the porosity of the correlation length, which is 0.4. And the directed percolation in 3D plus 1, 3D plus time, would be 0.58. In isotropic percolation, it's much larger. So we take this also as an indication that we have a directed percolation system here for sea ice. Next comparison, another transport property is the electrical conductivity. And this is here in contrasted to the permeability results that were shown earlier in the talk. Here's permeability. Electrical conductivity shows a different critical exponent, but they are related in a way that permeability is proportional to electrical conductivity times critical, or in this case, throat size squared. Yeah. This works very well for this data set, indicating again that percolation modeling is possible and useful. Finally, to compare this to earlier work, the magenta curve here is based on a similar approach where samples were centrifuged and then prints were produced on which permeability experiments in the lab were performed. And in this regime, our curve, the red one, shows very good agreement. And then, of course, we have the data in the low porosity regime close to the threshold. So this connects the whole data that has been measured before with our observations or with our computations. The blue dots are based on in situ experiments, but these are quite difficult because if you drain brine through the sample, you change the sample, so you never get you get a time-dependent permeability that is changing because the brine is melting through the pores and changing the pore widths. So these values are apparently much below because the porosity is the porosity in the beginning of the experiment, and in the end probably this porosity was lower. So it indicates that it's quite difficult to perform in situ experiments of sea ice permeability, and that this approach here via micro-CT imaging is much more trustful. The dataset. If you're interested to look into the dataset, it is published by Math2Market, and you also can, of course, you can download it there. You can also look at a video where the splitting of the pores is indicated, and a discussion of this application here is published in the Cryosphere this year, also shown on the dataset side. Yes, I come to the conclusions. The important results for young ice in this study are we get reliable computations of the permeability based on X-ray tomographic imagery. We find that the threshold behavior is related to a pore close off at the typical size of 0.07 millimeter, 70 micron. Critical exponents are consistent with directed percolation, not with isotropic percolation. This is important because there are really a few materials where directed percolation has been shown to be effective. Revised percolation threshold, before people were more talking about 5%, we find 2 to 3% for this young ice. Wide porosity range for the permeability porosity relationship where it is reliable. Future challenges would be different ice types, do such calculations. For older ice and coarser pores, we would very likely need larger sample sizes. And for geodict and digital rock physics, simulations of other properties, for example, albedo by something like Monte Carlo ray tracing. Albedo would be a really important climate relevant property that we would like to simulate on these images. Yes, thank you very much for your attention. Then I will close here.